Hello and welcome back. In this example, we were looking at textbook problem 1.25. You can find in chapter 1 in your textbook. And if you take a look at it, it is a trigonometry problem. It says we have a force of 40 newtons right over here. It's applied to an L-shaped bracket as shown in the figure to compute the twisting effect of this force about point A. And don't worry about the twisting effect. We'll get to that later on. But here's the problem they want us to do in just this part. It's necessary to determine the perpendicular distance, right? AB from point A to the line of action of the force. So find AB. So if we take a look at it, we can see we know we have a right angle here, we have a dimension, we have another angle here, and we have a dimension here. So first thing you need to do is set up the problem. Again, I like to set the problem up in standard homework format here. And in terms of it, we have given problem 1.25 and the diagram has shown. Now, I've simplified the diagram because I'm familiar with, I kind of know what I need. Your diagram may be more complex in the beginning, but in general, what we're really looking for is just sort of the bones of the problem. And this is what we have for given information. Again, that dimension 2.5 meters. In this case here, we have 35 degrees and this height up here. And we're looking for AB, right? A couple pieces of information. We know this is a right triangle, and although they don't show it, they do show it actually in the problem as with this box. That's a right triangle, because keep in mind it's the perpendicular distance. So if you take a look at this, you may think to yourself, we don't really have enough information here, but the reality is we do if we're careful about it. So first off, how do we get to AB? Well, we don't know the length BC. We don't know the length AC. We do know it's a right triangle. That's helpful. So we got to start with what we do know. And we know A to this point here. I'm going to label this D just so we have a good reference there. And we do know both AD and DC. So it turns out that we can easily find this line right here, this line that goes from A to C. Right? And the simple way to find that is using Pythagorean theorem. Because if you recall, a squared plus b squared equals c squared, right? We're actually looking for the hypotenuse. So we can rewrite that as c is equal to the square root of a squared plus b squared, right? And in our case, we're looking for AC. And that's going to be equal to the square root of AD squared plus the square root of CD squared, right? That side. We can put our values in. Square root of AD, which is 2.5 meters, quantity squared, plus our distance here is 0.6 meters, again, quantity squared. And if you go through and use your calculator, again, trying to do this all in one step is kind of helpful. Actually, clear that. I'm going to do a square root of 2.5 x squared plus 0.6 x squared, and then close parentheses and hit equal, right? And it's going to be about to be 2.57. Always good to check and think, well, does that make sense? Well, the fact is it's the largest side of a right triangle, so it has to be more than 2.5. And it's only a little bit more because this is a pretty flat triangle, so 2.57. And again, this is going to be in meters. That doesn't really help us too much. It gets us to that. It doesn't certainly solve the problem, but we can put that in there. So this is 2.57 meters. Now, again, we're looking for this distance here. We now have one side. So where can we go with that? Well, let's go and take a look at this 35 degrees. Well, we know this is part of a 90-degree angle. So if this is 35 degrees, we know that this angle, let's call this angle theta, has to add up to 90. So we know that 90 degrees is going to be equal to theta plus 35 degrees, or theta is going to be equal to 90 degrees minus 35 degrees. Right? So that's going to be equal to 55 degrees. Okay, so that's 55. We're getting somewhere. right? And you're like, okay, well, we still need some kind of angle. And if you work our way around, let's say we're trying to shoot for beta, right? So we have theta, we have which we now know, right? So that works kind of nicely. So let's look at what's this alpha. Can we find out what alpha is equal? Well, it turns out that we have all the sides of that right triangle. So we can use just about any technique. If we go with that angle, we could use sine, we could use cosine. The reality is, let's go with tangent, right? So tangent of, in this case, alpha is going to be equal to the opposite, right? In this case, 2.5 divided by the adjacent, which is 0.6. Or if you prefer, we can write it out. It's going to be equal to side AD divided by side CD, right? Well, we're really looking for theta, so let's manipulate this around. Tangent to the -1, or inverse tangent, and that's going to be of 2.5 divided by 0.6. We plug that in, right? And this is 2.5 divided by 0.6, close parentheses, hit equal, and we're going to get 76.5, right? 10 to the 0, so that's 76.5. And keep in mind, this is set to be degrees. That's something you got to be careful about with your calculator. Sometimes you get radians, gradians in there. We're going to be pretty much always working with degrees until we get to some rotation stuff. So this is equal to 76. Again, round it down to 3 significant figures, degrees. So plug that in up here. This is equal to 76.5. I'm sorry, 75.5. Let me check and see that. 76.5. I thought I had that written wrong. 76.5 degrees. Okay, so plug that in here, 76.5 degrees. So now we can find beta, because keep in mind, these angles are all complementary. So we know that beta plus alpha plus theta, they all add up to a straight line. So they have to be equal to 180 degrees. And if we take a look at that, we can change that around, that beta is going to be equal to 180 degrees minus alpha minus theta. And when we plug that in down here, beta then comes equal to 180. Slide that up a little bit. 180 degrees minus our alpha, right? We found that to be 76.5 degrees. And our theta we found to be 55 degrees. So we can just say 180 minus, put that answer in, and minus 55. Again, avoiding round off. And what you're left with is 48.49, right? So we're going to round that down to 48.4. I'm sorry, 49. So we're going to round it up to 48.5 degrees, right? Still doesn't get us to AB, but now keep in mind we've got a situation where we now know that this is 48.5. Right, so this equals 48.5. And we have the side, which is equal to 2.57, and we're trying to find this. So if you think about this angle, the opposite side of this, right? This is the opposite side, this is the hypotenuse. So what is the ratio of opposite to hypotenuse, right? You go back and you do your SOHCAHTOA, right? So the sine of beta is equal to the opposite, in this case it's AB, divided by the hypotenuse, which is AC, right? Again, manipulate this around while you're in the variable form. That way, we're really looking for AB, right? So AB, AB equals AC, which we know, times the sine of beta. Put our values in. AC is 2.57, again in meters, times the sine of beta, and we know in this case here, beta is 48.5. 2.5 degrees. All right. And if I go through and do this, I can say 2.57 times the sine of that answer and equals, and we get this equal to 1.92. And again, this is in meters, right? So that's AB. And if you recall, that's what they wanted us to find. And there's our answer, 1.92 meters. All right. Keep in mind, all of the answers for your problems are in the back of the book. So it doesn't exactly explain to you how to do the problems, but you can always go check on them to see if you got the answer right. And the day after your homework is due, I actually send out an announcement with the answers, so you can always check it and prepare for the quiz. As always, if you have any questions, don't hesitate to get in touch with me, and hopefully you found this presentation helpful.